Okay, so in this section, we'll continue our exploration of graphs of common polar equations. We've already seen these before. So for 3 cos theta, we know it's going to look kind of like this. And it's a polar curve. You guys have these notes, right? Trying to think here. Small points. The thick packet, I didn't hand it out.
On the one with the written notes.
Yeah.
It's part of that one.
Yeah, you have that?
Oh, yeah.
Yeah, okay, cool. So anyhow, we expect that to happen. I probably don't need to draw the polar coordinate system. But if I were to draw the polar coordinate system, it would look like that. Actually, I could probably just show you on here. Let's see. Homework. There we go. Polar graph paper. I have a whole bunch of polar graph paper for you guys. Yeah. So if I were to draw this, it would look kind of like this, right? You have that. You have that. And at pi over 4, 45 degrees, it should be 3 root 2, which is about, hold on. Yeah, 3 root 2 over 2, that's about 2 point something. Yeah, it kind of looks like this. Yeah, so anyhow. So let's come back to the notes again. So we expect this to happen. And we expect this to happen. Here we go. Okay. So this is a diameter of 3. That's a diameter of 4. Now, in terms of symmetry, this is symmetric about the polar axis, which we call theta equals 0. That's symmetric. So we're going to be talking a lot about symmetry today. So that's going to be symmetric about theta equals pi over 2. See how that cuts that in half? And cuts that in half.
No.
Just call it theta equals pi over 2. That's all. So what this means. So you guys remember we did odd even functions back in the day? It's kind of similar. There's a similar thing happening here. So this is symmetric about line theta equals 0. And that's symmetric about line theta equals pi over 2. Now, in order to test the symmetry, we would say this. The point r comma theta, for a point r comma theta on a curve, r comma negative theta is also on the curve. So again, 3 cos theta, which looks like this, right? And at 45, I know there's a point at let me think here. 3 root 2 over 2. Comma pi over 4. So if you think about it, there's also a point at 3 root 2 over 2 negative pi over 4. Why would that be? Yeah, kind of. I mean, so if I come back here again, actually, let's go to Desmos. That's probably gonna be best thing to do. Desmos. R equals 3 cos theta. Okay. So if I were to, and let's switch to polar. Okay. Okay, so you see R equals 3 is over here, right? Then you do pi over 4, which is right here, right? What would the R value be here? A little bit beyond 2, right? What's root 2 as a decimal, roughly? Divided by 2. 1, so 0.7, 3 times 0.7. So it probably makes sense. 2.1 makes sense, right? Okay. Now, what if I did that number, which is now Windows 2.1? What if I did negative pi over 4, which is now going to be down here? Yeah, there's a point right there. I agree. Yeah, negative pi over 4. That makes sense. Because that's also the curve. Okay. So yeah, that makes sense. All right. Yeah, as what Kingston said, top half, bottom half. You're correct. Right. The first one's on the top half of the circle, the other one's on the bottom half of the circle. Okay, that makes sense. Also, so that has to happen if you're symmetric about theta equals 0. That has to happen. The other one, which is not terribly obvious, this point will also be on the curve. Negative R, comma, pi minus theta. So in this case, negative 3 root 2 over 2, which we know is 2.1, now negative 2.1, and pi minus pi over 4, which is 3 pi over 4. Okay, coming back to Desmos again. Okay. So these are the same. Okay, so 3 root 2 over 2, and it was 2.1, negative is negative 2.1, pi minus pi over 4 is 3 pi over 4. 3 pi over 4 is right over here, right? 3 pi over 4 is over here. And if R is negative 2.1, first of all, locate over here, because R is negative, what happens? So does it end in the same place as this point? It does. These 2 points, or these 2 right here, are the same. These are the same. Okay. So that's another way of looking at it.
Can't you write that in like?
True, you can, yes, right. But what's going to happen is we're going to start looking at some really strange equations, and you're going to be asked to state the symmetry of that equation. And in order to test the symmetry, like we did for even odd functions, like I remember f of negative x equals f of x, or f of negative x equals negative f of x, that was odd functions. We're going to have to know both ways to test the symmetry out. We're going to need to do that. So sometimes if you replace theta with negative theta, you get r. Or replace theta with pi minus theta, you might get negative r. So we're going to have to use potentially both ways to prove the symmetry. For the next one, for 4 sine theta, we know it's vertical, the symmetry, right? Theta equals pi over 2. Now, in this case, you could have this. R, comma, pi minus theta, or negative R, negative theta. So let's explore that now. If I explore that, so 4 sine theta, right? Looks like this. Okay, what if I did pi over 4 again? So 4, actually, if I plug in pi over 4, I should get what? 2 root 2, I think. Is that right? Yeah, because remember, all summer do work and they choose to do it now. Okay. Right. So anyhow, yeah, it makes sense, right? Because sine pi over 4 is root 2 root 2. That's 2 root 2. Okay, so that's going to be probably coming back to Desmos or sine theta. Yeah, that makes sense. Pi over 4. So 2 root 2. Think about it again. What's root 2 again? 1.4 times 2 is 2.8. So that's 2. Yeah, pi over 4 is right here. Yeah, that makes sense. Yeah, because looks like this is r equals 3 right here where the arrow's pointing. That's r equals 3. That's r equals 4 where it's more bold. That's r equals 2. Yeah, that makes sense. I'd say that's raised to 2.8 and pi over 4. So you have to, it's a different mindset. You have to kind of think in terms of circles and angles, right? We do polar coordinates. But yeah, that makes sense. Okay. I'd agree with that. So now you're told that these two other points could be on the curve. You're told R. Oh, let me erase this up. This is confusing. That's from the previous. Let me get rid of that. Yeah. So you told R comma pi minus theta. Okay. So that would be 2 root 2, and that's 3 pi over 4. Does that make sense? At 3 pi over 4, which is right here. Yeah, is that about 2.8 for R? Yeah. That's a point there. Okay, I agree. Or you do negative R negative theta. So negative 2 root 2, comma negative pi over 4. Okay. Fine. Well, negative pi over 4 is hiding, is down here. But if it's a negative R value, what happens if it's down here? So now flip 180, so it gets back to the same place. So these are still the same points. These are still the same. So they're off by pi radians or 180 degrees. But you change R value from positive to negative. So that's another way you could prove the symmetry. So I just want to make sure we took our time with that. We didn't rush it. We could see, you guys see why that makes sense now? Why those are still points on the curve? So that's how you can prove the symmetry. That, if you're symmetric about pi over 2, right, you want the right side and left side. Or King said earlier for the polar axis symmetry, top and bottom half. So let's summarize this. How do we algebraically verify symmetry on a polar curve? If it's polar about theta equals pi over 2, then you need to have this. We just talked about it. R pi minus theta is on the curve, or negative R negative theta. So it means that if you replace theta with negative theta or replace theta with pi minus theta, you should get negative R respectively on the other side. That's how you can verify the symmetry. It should still yield the original equation. For polar axis symmetry, theta equals 0. If you replace theta with negative theta, you should get R, or you should get negative R if you replace theta with pi minus theta. So now what we're going to do is we're actually going to verify the symmetry algebraically for these two here. So what I could do is say, well, let's replace, so this has to be symmetric about theta equals 0. So R equals 3 cos. What happens when you do that? What's cos? Now, so this is where you have to go back and use your trig identities. Cos negative theta equals what? You guys remember? No. Cos negative theta. What's the identity for it?
No, just cos theta.
Just cos theta. It's an even function. Right? Isn't cosine an even function? It's measured about the y-axis. What's cosine 30 degrees or cosine negative 30 degrees? Same, because they're both in Q1 and Q4, right? So it stays the same. Because it yielded the original equation, it's okay. We're fine. Same thing here. Let's replace, let's use this one. Make our lives a little easier. Replace R with negative R, or replace theta with negative theta. What's sine negative theta? And negatives cancel. You get back to the same thing again. So that's how you verify. You verify in this manner. I'm not going to do the pi minus theta, because if I do pi minus theta, then what identity do I have to use to verify? You guys remember?
The Harrison fact.
Yeah, some different ones, which I'll give to you. Sometimes we might need to do that. Fortunately, the verification was fine with the simpler ways. But occasionally,
we do the verification of this or this, it may not yield what you're looking for, so you may have to try the other one. Sometimes you have to do that.
We'll see some situations like that, hopefully today or another class. All right, so let's move a little faster now. I think we're doing okay. Okay, zeros. It's kind of like x-intercepts. Okay. So recall that zeros of a relation of a or function in x and y correspond to the x-intercept of the graph. Define the zeros algebraic, we set y equals 0 and solve for x. We know this, right? Different for polar, though, a little different. The zeros of a polar equation correspond to the points at the pole. The pole's like the origin on the graph, because that's where r is 0, at the pole. So to find zeros of polar relation or function algebraically, set r equals 0 and solve for theta. Okay. So 0 equals 3 cos theta. And 0 equals 4 sine theta. Let's do 4 sine theta because I have that graph queued up already in Desmos. So of course, divide by 4, you still get 0. Where does that happen? Where would that be 0? On the interval from 0 to 2 pi. 0 and pi, yep. And this one should be pretty obvious. We know that should be at pi over 2 and 3 pi over 2. Okay. So now, it's a little tricky to see in Desmos. Let me clear the screen for a moment. It's a little tricky to see. I mean, obviously I see.
And this is so a pi, right? Like, okay, well, there's nothing going on here. It's just kind of confusing, right? Like, but what you can do,
This is the beauty about the TI-4 calculator. We'll have it go through it slowly. TI-84. We'll do it for a cosine. Mode. Polar. Polar. We'll do cosine 3. Cos theta. Window. I think I switched that to -6 and 6. Make that 0.001. I'll make that pi. Okay, so if I graph it,
notice that by the time we get to pi over 2, which is halfway, it's at the pole. So it only touched the pole by pi over 2. It's kind of hard to tell, but if I do it again to 2 pi, it's going to retrace itself. Because it already got one graph.
but what if I also went from, like, say, pi to 2 pi? Went from pi to 2 pi. Yeah, you can see by the time I get to 3 pi over 2, I'm back at the pole again. So that's solving, it's kind of like solving algebraically. That's what's happening. And 4 sine theta, you see the same thing. So those would be the zeros of the polar curve. Apparently, if you plug in 0 into 4 sine theta or pi, you get 0. Plug in pi over 2, 3 pi over 2, and the r equals 3 cos theta, you get the same thing. All right. Okay, let's solve a new type of curve. These are called limicons. Kind of funny looking curves. Okay, so what I want you guys to do is go ahead and try graphing each of these into either Desmos or TI-4 calculator. So we're going to graph all 4 of these and then generate the graphs and kind of observe what's happening. So go ahead and get a calculator out or use Desmos. I don't care. Either way is fine. Punch these in. Then we're going to make some observations about it. And if you do using a calculator, go from 0 to 2 pi for your window. Also let your theta step be 0.001. Let theta step be 0.001 so you can kind of see what's happening. Okay, go and try that.
Graph all of them out.
Do one at a time.
My other one. Bigger.
That's what.
Why does it do that?
Doesn't want to. Just does. Hold on. I messed up. Okay, that's kind of terrible. But kind of looks like a heart. Want to say so? This one's gonna look like this. Yeah, it's also terrible, but
So these have inner loops. And outer loop. C1 and 2 here, right? C1 and -3 here. See cosine. The cosine, I think, helps me understand that's symmetric about the polar axis. You see that right at the circle, right? That's 1, and that's 3. That's 2, and that's 4. How do you think these numbers are helping determine the size of loops? Well, what if I add 1 and 2? You get 3. The outer loop's 3. What if I subtract 2 and 1? What do I get? 1. Actually, let me take it back. When you subtract, you want the positive difference. What's the positive difference between 2 and 1? 1. Here, now, of course, I'd say -3, but take absolute value. The big absolute value here, what's 1 plus 3? 4. And of course, what's 3 minus 1? 2. There's a negative out front. So it goes that direction. So this,
it's kind of weird. It's kind of weird a little bit. Let's look at the other two. The other two can look like this. It's sine, so I expect it to probably be vertical.
Or
It's like if you walk, because I have been on the other streets. I think I'm right behind you, that's okay, it's on something. But I kind of read, you could make sure you take it and you don't. I think it's gonna be like certain foods for the ticket. But that's it, what? It's only one thing. So, I mean, it's. Things, they make some kind of stuff like that. Oh, this is gonna be kind of. Hey, it's sad, I have to smile for them. There's not a bit about, but one money is ready to go on, as long as. I had dairy, but. I don't know, what you got, but I don't know, here. You taking that out? Yeah. Are you looking at it? I don't know. They're not, they're not touching the button. They probably do send it. Like Friday, so you actually don't have. That is a lot of.
Okay, not the best looking spirals, but anyhow, how does sine versus cosine affect the orientation? Sine's gonna be vertical. Of course, I'm cheating because I'm looking at the answer key. for the graphs, but I know you guys can, and that's a horizontal. I'll explain that in a moment. The plus or minus, plus will be right, or negative would be left. That's for cosine. Or for sine, plus would be up, negative would be down.
The absolute value of the difference is how big the like is.
Right. So
Like what?
So essentially what's happening, I'm gonna give you a generalization in a moment. So 2 plus 4 is 6. 4 minus 2 is 2. This right here is determined by that number, where this crosses the 4 axis. 3 plus 4 is 7. 4 minus 3 is 1. The minus makes it go down. We have this.
we'll actually kind of do one of these. I think it would be good to do one of these slowly. Yeah, we'll do 2 plus 4 sine theta. We'll do that kind of slowly. So see how it looks. Okay, so yeah, let me tell you the generalization here actually. We'll look at more closely with part C. Okay. So for part C, I got about 10 more minutes. Okay. If it takes a range of 0 to 2 pi to draw the complete graph once, change your range from 0 to pi and view the graph. Okay. So let's do it right now. Let's go 2 plus 4 sine theta. Actually, let's explore that. So let's go 2 plus 4 sine theta. Okay, see what's happening? It does that. Then it creates the loop afterwards. Then it comes back down. So you see the order which is happening. The order does matter. You guys got to be aware of that. Now, if I went from 0 to pi, oh yeah. Oh yeah, I know we're gonna spend some time with that. Don't worry, it's new to you guys. So we do this. So it's doing the outer loop. It doesn't get to the inner loop yet. It stops right there. Now, what's happening? Let's make a little table here, so you guys understand what's happening. So theta r, remember r equals 2 plus 4 sine theta. Okay, we're gonna do 0. You could probably just find some place to do this, or you can just watch. I mean, I'm recording this. Pi over 4, pi over 3, pi. Yeah, we haven't done all the way to 2 pi yet. Actually, hold on, I'm losing my mind. Pi over 2. Here we go. 2 pi over 3. 3 pi over 4. 5 pi over 6. And of course, pi.
Is there like a way to graph it, or do you just have to roll the tables?
There's a way eventually, but for now we're just doing this so you guys get a better understanding of it. So if I plug in 0, what's sine of 0? 2. Well, sorry, sine of 0 is 0, but 2 plus 4 times 0 is 2, right? We expect 2. But I put in pi over 6, sine pi over 6 is 1/2. 4 times 1/2 is 2, so we have 4. So it kind of makes sense. I mean, it's hard to tell, but
Actually, if I go to decimal, it's probably a little easier. But if I do plug in 5 or 6, it looks like the radius would be about 4.
Actually, I'll go to Desmos after I finish this table. Pi over 4, sine pi over 4 is root 2 over 2. So you have 2 plus root 2, I think. Wait, no. Sorry, 2 plus 2 root 2. My apologies, you're right. Pi over 3. And of course, 6. So root 2, I know is 1.4 times 2 is 2.8 plus 2 is 4.8. That's about 4.8. 2 root 3. That's like 3 point, was about 5.4. And then you have the symmetry, right? That'll be, it's still the same thing here. Still the same thing here. Still the same thing here. And then that's going to be back to 2. So if I go to, so to answer your question, Charlie, like why is it doing those loops and this and that? It's really just the nature of the equation. That's what we're seeing. So it just does it. We go to Desmos. Okay. Let's do 2 plus. Okay. Okay, that should help.
Yeah, so 0, 2. Okay, so it starts here. Oh, sorry. 2, 0, sorry. R is 2. That's where right here. When you're at theta equals 0, there R equals 0 on that circle, right? The constant of circles is 2. Circle of 4 with pi over 6. So pi over 6 is right over here. And a circle of 4, 1, 2, 3, 4. That makes sense. Okay, cool. That's about 4.8, I think. Is that right? Yeah, because that's 1.2.8. Yeah, 4.8. So pi over 4 is right over here. Yeah, that makes sense. That R is about 4.8. That's 5, so a little bit below 4 or 5. That's 3.4 plus this 5.4. So pi over 3, 5.4, it makes sense. Okay. And then pi over 2, you get 6. And you kind of get the same thing as it go all the way around. If you're at pi radians, you're on the circle of radius of 2.
It all makes sense. We're seeing why that's happening. Then we'll look at the inner loop after that. Try.
What if our theta value that we're putting in, typically like that line goes through 2 points, there's an inner loop. How come it only produces that one outer loop? Like pi over 4, if you went one, pi over 4, it goes through there.
Yeah, it goes through. Yeah, pi over 4 goes through here, right? Okay.
Yeah, then also would overlap with that one.
That's probably because it's what's going to happen by plugging, like, say, 5 pi over 4 is probably a negative R value, and it's going to go backwards. Let's fill up the table to answer your question.
We'll fill it out. So going back to the notes again, what's happening here is that if you go from 0 to pi, what do you notice? You just get I want to say top half. You get the portion above theta equals 0, or the outer loop. That's what we got. Okay. So now you're asked to determine the zeros of the function. Let me get rid of this here. So replace R with 0. You should get negative 1/2 if you do everything correctly. Where does it happen? At 7 pi over 6? At 11 pi over 6. So that's where it touches the pole. So we have not touched the pole yet, right? We've not touched yet. All we've done so far going back to the calculator.
Right, we've not touched the pole yet. So going from 0 to pi, we just got the top half or part above the polar axis. We've not generated the polar inner loop yet. When do I start producing an inner loop? So to answer your question, in case you ask, like, how do we know, or someone asked me, Lucas, maybe, how do we know, like, how to do this without, like, making a table? You gotta find the zeros. You're touching the pole, that's how you can tell. So we're not touching it until we get to 7, 5, or 6.
So here's where it gets real. This is why the graph calculator is kind of cool. Let me go ahead and clear this for a moment. Let's go to window. Let's go from pi, where I'm touching the polar axis, we know that, to 7 pi or 6 where I'm touching the pole. Ah, crap. What do you think you're going to generate? That little like dip there, right?
And it's hard to tell. But it's gonna be that little dip from here, from -2 to 0. That's what it's generated, right? Then we're gonna start creating the inner loop.
The inner loop is only determined from where it's touching the pole. It's touching the pole 7 pi or 6 and 11 pi or 6. We already deduced that, right? So if I go back, let's do this from 7 pi over 6. 7 pi over 6. And I really want to be very slow and deliberate about this because I don't want to just rush this. Like, you really have to have a deeper understanding of this, especially if you're going to be doing this next year. Let me clear. Yeah, see how it's producing that inner loop? By the way, what's halfway between 7 pi over 6, 11 pi over 6? Which is 9 pi over 6, or 3 pi over 2, right? But do you say 3 pi over 2, or see 12? That's okay. No, it's 3 pi over 2. Do you say 9 pi over 12? No. Halfway between. Sorry. Not half of 7 pi. Sorry, halfway between 7 pi over 6 and 11 pi over 6 on the inner circle would be 3 pi over 2, or 9 pi over 6, whatever. What's sine of 3 pi over 2? Correct. So if I plug into my equation, what's my equation again? 2 plus 4 sine theta.
Think about it. If I put in 3 pi over 2, what's sine 3 pi over 2 again? -1. What's 2 plus 4 times -1? So going back to
The polar curve. I'll go to Desmos now, kind of going back and forth.
if you think about it, so my R is 3 pi over 2. Sorry, my theta is 3 pi over 2, but R is -2. So I'm not going to be here because when R is -2, what's going to happen? Comes back up here. So that's why this loop gets created that way. Because all these sine values from 7 pi over 6, 1 pi over 6 are all negative. So you're having all these points here. So to answer your question, part like how can we finally see, pi over 4, such as this is really going to be at -5 pi. Sorry, 5 pi over 4, but negative R value. There's a negative R value. We'll fill out the table in a moment. And so what happens? All these get delivered, helping you generate that inner loop.
That's how the inner loop gets generated. Okay, bell's about to ring, so I'll stop there for today. I'm almost inclined to say no homework over the weekend, just because I don't think I've covered enough to help you guys do the homework.
Let me take wait. You don't think you can probably do page 1. You do page 1. Probably do page. You can't do number 2 yet. Yeah, so the homework will be adjusted a little bit. You do a little bit. It'll be small homework. So yeah, do pages 1 and 2 of the homework. Yeah, that's fair. It's nailed that. Yeah, so set the equation equals 0. Solve for theta. You get your 2 values. See maybe between those 2.
Oh, that's it.
Yeah, but I don't want to just say that one. But we need to spend a little more time with this. We'll spend more time at next week. So, yeah.
Thank you.
So it's a lot of catch up.
Well,
No like to catch up.
high quality bad.
That's good.
Thank you. You're a grown boy.
You're welcome.
Yeah, I know, I was.
Thank you, Missy. Thank you so much for the super.
Oh, of course, yeah.
Y'all throwing this stuff away?
Sure. You don't want to do that. Actually, I might need one of the bags, but
I was just like.
You don't wanna bring me some?
you want, I don't care about sauce. You can take this off for a month. Guys,
We're
gonna start doing.
I told some of my students that I'm gonna just take my students to live them, so.
Okay.
I think I'll be able to fit them all. So if anyone comes in here, send them over there. If I get over full, I'll put some back over there. I think it just,
Okay, so what can we go to? You want the parent room or?
no, it's really.
That.
I got it.
Yeah, if you mind throwing that away, I'll put the fridge downstairs. You can take sauces. Sure. Okay, we'll try it.
Yeah.
Thanks, sister.
Welcome, of course. Still doing it now. It's a little hard though, 'cause I gotta wait forever. It's my, I just use the app on my phone, it's easy. Especially after having Chick-fil-A, if I'm forced to, yeah, why can't I do anywhere else?
Chick-fil-A, made my day. Yeah. Now I don't want to do anything else. It's easy being there. Are you going to your work meeting? What? Are you doing classes? I'm like, thank you.
Welcome.
Thank you.
All right, let's get this showing the code.
I,
All your students are gonna come to your.
yeah, so they don't necessarily know or won't remember, but I think I got 13, 12. And how many you say you have here?
9.
Chick-fil-A over well, I'm sure.
Oh, yeah.
How to win friends and influence people.
Exactly. I like to see where you like one. I already worked out the rubric. Okay, she shared what I got.
We're going over the other room, 218. Yeah.
There you go.
Here's Davis's class. Yeah, we go to 218. We're gonna start it out. So you got that. I'm going straight here.
Great.
Yeah.
Hi, you still like it?
No.
Oh, you were, oh, you're. Well, how are you done?
Was it sorry? Sure. Yeah. Okay, if you make a mistake, it might not pick it. Oh, yeah, you can use the. Okay, let me get you guys started. There you go, Marco. Yeah. So. Yeah, right. I don't think we really see that. Okay, I'm gonna close this window. It's actually loud. All right, good luck, guys. So it's about 2:12. We'll say 3 o'clock. You guys should be wrapping up.